Good morning, everyone. This is Reza Tegabi from Itasca Consulting, and I will start my presentation of KUBRIX version 15 today. KUBRIX version 15 is the continuation of the KUBRIX family of software that saw its inception in 1995. It's been nearly 20 years that KUBRIX has been around. It is an automatic, primarily grid generator. In the last 3 years, an interactive grid generation capability was added to this program. It is a general purpose grid generator or grid generation toolkit for the entire computer-aided engineering field, in particular Itasca software. KUBRIX works in concert with CAD systems. It's been implemented in many CAD systems around the world, including CATIA and HyperMesh and Patran. We will be talking today about its integration in Rhino, which is what we like to use here at Itasca. KUBRIX for geomechanical applications is named KUBRIX Geo and is sold as KUBRIX Geo. The interactive component of KUBRIX, which, as I said earlier, was introduced 2 years ago, is called Block Ranger and is available separately. What's new in version 15? A slight improvement to the hexahedral meshing capability of KUBRIX through a simplification of its auto-hex meshing GUI. What we call a geometric associativity, which allows you to specify boundaries, faults, special surfaces in the CAD and expect to see the associated zone faces or element faces appear in your analysis software, in our case FLAC3D. Sense that you will not need to use ranges in order to specify a surface, a complicated surface. You can define it during CAD, and after meshing you will see the surface appear as a face group. Thirdly, edge resolution control in Block Ranger. As those of you who are familiar with earlier versions of Block Ranger 1.0 are familiar with, you will notice that in the new version we have added control of local resolution. And finally, we now produce 3-deck models with Block Ranger as well. It provides us with essentially a fourth capability for generating models for 3-deck. Essentially, KUBRIX is a toolkit that also promotes a certain workflow. The notion of workflow is important because data is generated from the time that crews verify or make measurements on core all the way till an executive reads an executive summary that backs a certain proposal in a report. That workflow, a certain part of it which we own, is the part where surfaces are received and a mesh is generated, read into the analysis software, boundaries are set, materials are set, and plots are produced and reports are written. So in general, in our workflow, the reason why we would like to use an automatic mesh generator or an interactive grid generator with Rhino is because, first of all, grids, which is the part we are interested in, are volumes in general. For our purposes, volumes are bound by surfaces, so it's easier to work with surfaces than volumes. As long as these surfaces are closed, we are properly handling volumes. In Rhino, which is a solid modeling or essentially modeling software similar to maybe AutoCAD and SolidWorks and CATIA and ProEngineer, Rhino is one of the simpler and the most affordable and also the most advanced one, to our opinion, In that program, you can assemble and edit surfaces. You can receive curves, portions of meshes, and topographies, contour lines, bring them into Rhino. And Rhino provides a collection of surfacing tools that allows you to create surfaces and surface meshes and essentially create what you need. The approach for grid generation is really twofold. One, which was traditionally the KUBRIX approach, is called automatic grid generation or mesh generation. And you, as the user of KUBRIX, create initially a triangular surface that is closed. It may contain intermittent faults in between, in there, but it needs to define overall a closed region of space. And then you click on an icon that you see on the right side, the first icon to the left on the KUBRIX toolbar in Rhino, which brings up a set of parameters that globally define the characteristics of the mesh that you intend to produce. In interactive meshing, as its name indicates, you create the mesh by hand. It's not as detailed and as tedious as creating meshes with a command line, but you define overall the position of the corners of blocks of meshes, and then you do that as contiguous solids of a certain types in Rhino in our case, and click an icon, which is the second icon that you see from the left, which is the red KUBRIX icon in the KUBRIX toolbar in Rhino, to produce FLAC 3D and 3-deck blocks. Now, a question of nomenclature. We call block generation for 3-deck grid generation because the grid generation that 3-deck does internally is essentially a subdivision of the volumes, these blocks that we give it. So for all intents and purposes, a 3-deck grid is essentially a coarse grid made out of tetrahedra that are always, therefore, convex. Interactive meshing is a method that requires quite a bit of skill, in the sense that you need to envision the various mesh blocks that will constitute your final mesh. It requires a certain organization in your model, whether your model is composed of mesh blocks that are the results of sweep operations or 2.5D extrusions, as some call it, whether the geometry can be put into a number of relatively simple blocks, a number maybe not exceeding a few hundred, considering that the unit of work is essentially a block of mesh. Therefore, grid generation interactively is a rather tedious operation, but which has, as a reward, provides you with the possibility of controlling the grid distribution, the local density, the orientation, and the sizing of the elements. That's very important, especially for civil engineering applications. As you will see in automatic meshing, that capability is somehow lost. You let the boundary of the computational domain, so this is the next picture here, the boundary of the computational domain lets you essentially determine the domain in which a mesh will be produced. You simply have a number of opportunities in terms of global quantities, what global density you like, what the global type of element you like, etc., etc., and the mesh is produced accordingly. So automation means to some extent less control, certainly less local control. Interactivity, on the other hand, means much control, less automation, more tediousness, etc. We have been talking about geo applications. Of course, KUBRIX is used in a variety of other contexts, especially mechanical engineering, mostly automotive, mostly in Korea and Japan. Here are some examples of planetary gears here and electronic connectors, crankshafts and covers and wheels and pistons and brake pads and seats and various electronics and bearings and plenums here. But in these applications, the grid has been subdivided by humans, so there has been quite a bit of human interaction in terms of decomposing the mesh initially and reassembling it afterwards. But that is something that folks in the automotive area like to do. Select customers of KUBRIX outside of the many ones that we know in the geo area are mostly automotive and electronic companies that use this program. New in version 15. One aspect that I would like not to stress too much upon is the simplification of the auto hex meshing. It may be a bit misleading. There has been really no revolutionary improvements in the KUBRIX auto hex meshing. It still requires quite a bit of skill and experience. Many in the industry, mostly in the mechanical engineering area, have more experience than I do in using KUBRIX for this type of application. I'm just the developer of it. And so those who have spent time learning this program have managed to create very complex meshes with this. What we have done in version 15 is simplify, reduce the number of parameters in the hex meshing, or what we call structured hexahedral meshing of KUBRIX, to make life a bit easier. And we have included an initial surface remeshing that in some cases, not all cases, improves the chance of obtaining a mesh and improves the quality of the outcome. But again, I would like to emphasize that this is not a groundbreaking showstopper of an improvement to the hex meshing capability of KUBRIX. This will come, we hope, in KUBRIX 16 next year with a completely different canonical block decomposition methodology, and which we hope that will still make KUBRIX the leader in hex meshing. It is currently the only automatic hex mesher that is available right now, but certainly not perfect. I would like to now focus on the two most important improvements in KUBRIX 15. One is resolution control in Block Ranger. Essentially, Block Ranger is a plugin to Rhino. We chose Rhino because we wanted to expedite everything that has to do with representation, graphics, selections and widgeting and dialog boxes, and focus on the engine to generate these interactive meshes. And that was done through the creation of a plugin which is installed when you install KUBRIX Geo version 15. That installation then makes sure that the plugin is placed inside Rhino and the icons appear there, and you can then select the solids that you would like to process into mesh blocks and click on the Block Ranger icon to produce the resulting mesh. Very quickly in this slide you can see a very simplistic, a simple process that shows in this case a underground cavern defined by a number of contours. Within Rhino, these contours are turned into this surface that you can see here in a brown shape, and the outer boundary of the cavern is also specified. As a result, we obtain 1, 2, 3, 4, and 5 solids, which at the push of a button within Rhino, by clicking on the Block Ranger icon, is turned into a grid. resolution control manifests itself in the following manner. First, we create a collection of solids in Rhino as we did in the earlier slide. In this case, then, we select all our solids and click on the Block Ranger dialog box, which provides us with the three control parameters, which are all set to a default value. You can accept that default and you obtain a mesh that is maybe frankly acceptable in most cases, but if you prefer to refine certain areas, you use the extract edge icon that is available in the KUBRIX dialog box, and we will talk about that a bit later, and you select on the edges that you would like to control. So this is one, this is another one, this is another one, and you set the resolution of these edges, in this one say to 3, or this one to 15, and this one maybe to 8, and again run Block Ranger, this time making sure to select the solids but also the edges that bear those resolution numbers in order to obtain then a mesh that complies with those resolutions. Another novelty in Block Ranger is the ability to produce 3D models. So at this point I would like to show you a canned video that we have prepared here. This video shows the main lines of producing a grid using Block Ranger. To do that, we are often given a number of points or some contour lines as a starter. In this case, I chose to just simply use a mesh as our starting reference geometry. There is no need to use a reference geometry or a mesh, but simply here the customer has given us this object, and we start by creating a number of construction lines, construction curves that we will later on use to create the surfaces. And as you can see here, I've used the arc command in the curve menu item, and then I have used a line segment command to continue to extract or draw over the mesh a number of lines that I will subsequently use in the creation of my various surfaces that will lead me then to the final Block Ranger mesh. Once these lines have been extracted, we will now create surfaces that span on these curves, and we get rid of the initial mesh. So what we have left on the screen is essentially these lines, and we start creating surfaces in between these curves. These will all be described in our user manual. There is a text version of this video that should be available very shortly. But as you can see, we have created a curved surface using the loft command. And again, using the loft command, we have created another slanted planar surface. We created a horizontal surface using the planar curve command, and using the same planar curve command, we create a sequence of planar surfaces that essentially define the various sides of the computational domain. We continue to create the various surfaces that bound volume of interest. At the end, we join all these surfaces, leaving the bottom surface open, and we got rid of the curves that we used. We joined the surfaces and used the solid cap planar holes to cap this closed surface. Now this is one solid. Of course, it would be nice to be able to create from that one single solid the mesh in automated meshing. That's the surface that we use for meshing. Here we want to control the grid distribution. So we will go about this by subdividing this solid into a number of smaller solids. Here I am drawing a number of lines that will enable me to split these surfaces, the surfaces that define this solid, into smaller surfaces that define smaller blocks, so as to produce a number of smaller solids which would then later on be meshed into separate mesh blocks. As you can see, interactive grid generation, at least with Block Ranger 1.1, is rather tedious, so you need to be aware and assess your time and your requirements fully before undertaking this kind of grid generation in an interactive way. But here we exploded the surfaces that constituted this closed volume into a number of different surfaces that we colorized separately. The curved surface has been split into two pieces now, and you will see later why we do this. And similarly, we are splitting this green surface into two pieces, and we now select that rectangle and that quarter cylinder and extract, duplicate the boundary of these two surfaces in order to create two closed curves that then we would like to join using the loft command. Here we need to tell the program which corner has to be attached to which corner. As you can see, then the lateral surface of this solid is produced as a gray surface. By joining this gray surface with the two surfaces that cap both ends, we obtain one nice solid that appears in gray. Similarly, we are going to create the adjoining solid, again in a similar fashion, by cutting the opposing rectangle into four smaller bits, and rectangles are both selected. One rectangle here is selected, and the curved surface that is supposed to face it. We extract their boundaries, and we use the loft command. Again, we need to tell it to connect that point to that point. We have to physically drag that connection point and say, go ahead and create a lofted surface. That surface is, of course, just the lateral surface, including then now the two original surfaces, and joining them together, we created now our second solid. And so on for the last solid of the upper layer of this model. We accordingly we use the same lofting command and obtain our solid. I'm going to a little bit accelerate this demo here. For the interest of time, I have created essentially three solids on the top, and now I'm going to create another solid in the bottom here. I throw away that mesh that I had kept originally, and here you can see that what we have right now is one solid, two solid, three solids, and the surface here and a straight line here that we drew that will be used then later on to create the to extrude that surface. And I will accelerate this here, showing how we extract these other surfaces plus this surface, and we extrude them all in the direction of the line segments in a straight manner, and we have now this way then created all the solids that we need. We're going to splice or slice this odd-looking solid into a quarter circle and a parallelepiped, and now we have a nice collection of solids, and remove all the extra curves. And this collection of solids, if we colorize it, we see that we have 8 solids. Now we have this solid, we select them all, and use the we can also organize them. We can decide that the top solids are going to be placed in a layer called something, and then this lower ones will be placed in another layer called lower, and then finally the bit on the lower right will be placed in lower, called lower 2. And this, we are doing this in order to make sure that once the mesh is generated in FLAC3D, the various layers become separate groups in FLAC3D bearing the same names. So we run Block Ranger with all defaults here, and you can see that the mesh has, select this and click on the Block Ranger command here, and I'm going to slow down a little bit this presentation. It says that 8 solid have been processed, so we ran Block Ranger with all defaults. We didn't set any number, and that has been a mesh, a FLAC3D mesh was created, but also at the same time a blockranger.wrl file was created, which is essentially a representation of that mesh in forms of quads. And you can see now the mesh that was produced. You don't need to stay in FLAC3D to see that. You can see that there is a little problem here, meaning that the blocks of the quarter circle do not match, the grid points do not match, leaving some gaps. So obviously there was an error in this meshing, and the reason for that is that the quarter circle needs to be split again into 2 8th circles for the faces to match. So this will become clear a bit later. You can see here that this one single surface of the cylinder is supposed to match 2 curved surfaces of the other section. So we get rid of these meshes that we just read, and we go back to our solids. And now the first thing that we would like to do, we will split this quarter cylinder, or at least its lateral surface, its cylindrical surface, right now into 2 pieces. So you will see here that now this surface, the curved surface that is facing us, will be split in 2 pieces, either by a line here that we draw from the center of the top curve to the center of the bottom curve, and we use the split operation to do this. And after doing this, we get rid of the line that we used, and these are now the 6 surfaces that we have. I've colorized them separately, so you can see that now this object is very similar to a box topologically. Now this lateral surface is made out of 2 surfaces, which should match the 2 surfaces of the other solids. Now, so in the overall number of solids in the model, we haven't made any changes, but the lateral face of that quarter cylinder has been split in 2. And again, every solid goes into its right layers in preparation for meshing for FLAC3D, so that the resulting mesh blocks belong to the right groups in FLAC3D. At any rate, we select all our solids, we click on a Block Ranger, and a mesh is produced. It also creates a WRL file, so we can either open it in FLAC3D, or we can just read the WRL in Rhino here and overlay that on our mesh and use the colorize to distinguish the various groups of this mesh. And now you can see that we have a pretty good mesh, although it may be desirable that this cylindrical part does not feature these highly degenerate quads at its corner there. So what we're going to do is that we're going to take that quarter cylinder solid and split it in 2. as opposed to this one single quarter cylinder. So we will create 2/8 of a cylinder. You will see that here. First, we select the solid in question, which is this one. We hide everything else but that. And in a top view, draw a line that goes from the center, from the pole, all the way to the boundary. And this results in, with the command called wire cut, allows us to create two nice solids out of these single solids, so 2/4 of cylinders. Now, again, we put that all together. We are sure here that these two new solids are in the right layer, the upper layer, lower layer, and the lower 2 layer. Again, we run Block Ranger, and again, this time reading the WRL file, and this time, sure enough, the grid looks definitely better and does not display that degenerate looking hexahedra that was occurring at the corner. You can see that the grid is a bit more radial and the grid lines are more orthogonal to the boundary, which is what we want as engineers. We want good quality elements. Now, when we look at this mesh, we see that there are areas that are very sparse and areas that are very coarse. We would like to have a hand at improving these grid distribution, which up to now the global quantities that the Block Ranger command line offered were not sufficient to satisfy. Here we are looking at this mesh, and we are going to select certain edges on the surface using this icon in the KUBRIX toolbar. I selected a number of edges, so at this time I selected one edge on the left side, and I set that edges, as you can see it here in black on the left, I set that edges property to in the property page of it, I set a number, which is the resolution that I would like to see for this particular edge. And now I look at the mesh and I see that now the number of elements in this upper layer altogether has gone from 3 to 6, which is what I have, and of course it propagates throughout the whole mesh to go completely to the other side as well. Again, now I want to control this edge. As you can see, I selected the edge. The dialog box of the property comes up on the right, and I set a number here of for what I would like to have. I set it to 8, I believe, and right now we have 4. And now when I generate now my mesh, you can see there are now 2 edges that have been specified. I select the entire thing, not only the solids as we used to do, but also the edges that now bear the resolution that needs to be handled. And you can see now as the mesh is produced and colorized again, you can see that the new mesh complies with the resolution that we wanted. A third attempt here is to change the resolution of the lower layer from 3 to a larger number. Again, KUBRIX Block Ranger will automatically propagate these resolutions throughout the model. I extracted a new edge using the extract edge icon and set the, so we, as you can see in this model, we have now 1, 2, 3 edges that have each prescribed resolutions, and we run Block Ranger, again making sure that we select these edges as well, and the resulting mesh now complies with the resolution that we wanted. And you can see now that the lower layer has a resolution of 5 instead of the default value, which was 3. So this is the end of this tutorial. Geometric associativity is the next topic and final topic that I would like to bring up, and I think this will be very much of interest for folks who use KUBRIX in mining application. We have an example here of a mining application with a complex geometry, a topography that was complex, and faults that were received as the XF files faults that were barely intersecting. And as you can see here, and I will go into a bit more detail in the subsequent video, you can see here that the KUBRIX dialog box that appears in here has a new component. In the lower part, you see in the new keywords area, you see dash fault f1.stl, dash fault f2.stl, dash fault f3.stl, etc., etc. So all the STL files that that participate in the creation of this model, if they are separately invoked, they will result in separate face groups in the resulting FLAG3D grid. So you will see a FLAG3D face group called f1.stl, f2.stl, etc., etc. So we're going to go now into this particular video. I'm going to try to be a bit faster. We are not going to linger too much in here, but I want to show you really how we now do this kind of model. It's very interesting, and for those who may have assisted to my presentation a week ago about surfacing in Rhino, they will see that in this approach, I'm showing here an entire workflow. We have received from the customer a number of meshes, and these meshes are all rather imperfect. We have a mesh that represents the topography and faults that intersect and go through the topography. We are going now to convert every single mesh that we have in this model into surfaces and only work with surfaces. Starting with F1, which was fault number 1, I am going to use the command called patch under surface patch and set its U span and V span to 10 and its stiffness to 1 to turn that mesh into a surface that is certainly much better behaved than the original mesh. And by using surfaces, we will be able to combine them nicely with all the tools that Rhino provide us and considerably reduce the time it takes to produce this type of meshes. Again, now I am moving on to fault number 2. Again, used the patch command to turn that fault. I have gone to fault number 3, 4, 5, 6, and now we're going to do fault number 7 in the interest of accelerating this process. You can use patch. Those parameters that I've chosen are just indicative of this particular example. You can choose stronger parameters. It will produce coarser or finer surfaces with more complexity or less complexity. Here I'm using the same number resolution in the U and V spans, and now I deal with surface number F9, and I again turn that into a patch and make sure that each patch goes into the layer where this fault was located. Again, this is going to be a tutorial that will be shortly available. For the topography, I can use patch, but it will result in a rather odd surface, which is not well adapted to the application we have in mind. You will see that the resulting surface is highly goes through various gymnastics in order to comply with the geometry, and you can see that in many areas the surface does not match this rather complex topography, which we absolutely need to comply with. Here we're going to get rid of this first surface that we have created through the patch command, and instead revert to the drape command, which is our favorite surfacing tool. And before we drape this surface, we are going to define the computational domain, which is going to be this box here. That's where at the end we would like to create our FLAG3D and 3-deck model. After I defined that box and I zoomed in the neighborhood of that box, I'm going to use the drape command and draw the rectangle that then will represent the draped surface. I will hide my initial mesh and then you will see here the single surface that is produced that is supposed to represent that mesh as a surface. So our mission here is to turn everything into a surface. We have turned all meshes into surfaces, and you can see that including the computational box here, we have a collection of surfaces, and we just get rid of the meshes that we have. So this is the configuration of my model at this time. Nothing has been done, no intersection has been done, all the meshes have been turned into surfaces, including the topography, and we have one additional surface, which is essentially the computational domain. But also, at this time, I select everything and click on this command called non-manifold merge, which you can see it's the penultimate icon on the KUBRIX toolbar. By doing this operation, I created one single non-manifold surface, and you can see it looks quite ugly. Some of its surfaces are transparent, so there is something wrong with that. And in fact, if I use the check command, I will notice here that this single poly surface, which is the result of the fusion of all these surfaces, is not valid. In order to render it valid, we're going to use a command that the folks at Rhino has written for us. It's called test extend slits. Again, this is described in the tutorial that you will see shortly. And by using this test extend slit, it will transform individual surfaces into valid surfaces. And now the resulting poly surface, this is a poly surface that you see, this resulting poly surface is valid by clicking on the check command on the right side. Now that we have this valid poly surface, I made sure that I made a copy of the various surfaces that I used earlier before I did the non-manifold merge. So now I paste those surfaces back, because in the non-manifold merge I lost my surfaces. Now we are going to so-called prune this poly surface, i.e. remove the surfaces that we don't need, leaving only what we need before we can mesh this thing. So I use the extract surfaces and make sure that I just extract them. Extract the copy. You can see by selecting these ones, everything is outside, so I select this and delete it. So I've gotten rid of that particular surface, and I will progressively remove all the surfaces. This again may be a tedious operation. Again, I chose the wrong surface. Again, I do that again, extract surfaces. Now I've selected the right surfaces to extract, and I delete these, and so on until finally I have removed every single surface that sticks out of the computational domain. Same thing here. I'm going to accelerate this video a little bit faster, and you have to inspect this. You have to use the lighting. You see, this is something that is requires quite a bit of care. For those who are interested, we do provide these as services at Itasca. So in case you need some help, we can certainly help you with that. Again, in this case, I remove the this additional bit of surface that remains. So we created a nice surface that doesn't have any excess surfaces out of it. Now we are going to continue this pruning process by removing the excess surfaces that are in the that are essentially located above the topography. So again, extract surfaces. I just select by judiciously choosing my window. I removed a number of these surfaces. There are still more left that need to be removed. I'm going to accelerate a little bit the video here for you to see how I remove additional surfaces. You have to be very careful not to remove any internal surfaces. After all, what will be left at the end needs to be closed. So you want to make sure that the surface that we obtain at the end is watertight so that it can be meshed properly. So we continue, and at some point we may even use the other rendering tools that are available in Rhino, using shadows even, maybe to make sure that nothing exceeds the topography. You can see there are bits and pieces of triangles or surfaces that stick out, and now we have our we're getting close to our final poly surface. So what we have at this point, once we have removed all these things, is one single poly surface that now gives us the guarantee that if we mesh this, we will get one nice non-manifold mesh with no bad intersecting, doubly defined, dangling nodes, etc., etc. This is the virtue of using surfaces in our work instead of using meshes. I used the show edges command and asked it to show me the naked edges, and you can see that the naked edges appear in pink. So if there are any naked edges in this surface, there are intended edges that are due to the surfaces that are inside, the faults that are intermittent. Now we mesh this thing, we chose a number of parameters, and this mesh now, the poly surface that resulted in this mesh, we place it into a layer that we call poly surface, hide it, and what is left now is this mesh, which has really no problem. There may be a few left in there, but we verify now that this mesh that we obtained has complies with the requirements of KUBRIX, and we can see that all the free edges that are in this mesh are free edges that are intended intermittent free edges of the faults that are inside the model, and that's okay. Now, at this point, before, we would just go ahead and mesh this with KUBRIX and obtain a mesh, and then later on we would have to use ranges to obtain the various face groups that will become interfaces. Or we would put the entire outer boundary as the input and the entire inner boundary as one single mesh, and let KUBRIX subdivide that into hundreds of little patches. Here, what we did is that this mesh, we just exploded it, and Rhino will subdivide it into all these patches that we can easily assemble without having to deal with individual triangles. We did a welding operation at 360 degree before that was very quick, and you may not have seen this, but this video is just simply a pretext to show you the workflow, and it's not designed to be used as a tutorial in itself, but you will see in the written tutorial how exactly to do this. But as you can see here, by exploding the mesh automatically obtained from the non-manifold surface, we obtain essentially various surface patches that we can organize by ourselves. So that's what we're doing. We organized and extracted all the outside patches, and now the parts that represent the topography very quickly. We are doing that very quickly in order to create a sort of outer mesh. So we have to look for bits and pieces that we may have forgotten. And so this bundle of meshes here is one thing. You know, there's some exceeding, some of the initial meshes are still here that we need to get rid of. But the model essentially now is composed of this pink outer part, and we notice here that there were a number of meshes that were not accounted for. So I place them into the outer mesh. So we organize this mesh that we have just created into essentially one external mesh that we call outer, that I'm just here preparing. And now I'm going to hide that. I'm here inspecting bits and pieces of this outer mesh that have not been completely captured. I just add this final bit to the outer mesh here. So this is now constitutes the outer mesh, and the outer mesh is now complete and closed. If I do a check on the edges of this, you will see that this outer mesh has no free edges, so this is good, no naked edges, so that's good enough. Now we hide that, and the next thing that we will do, these various mesh patches that are inside, we're going to put them in their appropriate layers, and that is a tedious operation, but you can see it's quite straightforward but time consuming. This entire tutorial was filmed almost in real time, and this operation here may take half a day to 1 day, and used to take us about 3 months to create these models. And those who are in the petroleum industry using GoCAD and Diana and so on, or Petrel, are also familiar with these timescales. So here we really have really an edge by using the Rhino workflow. So what I did here is that I went back to the layers and just turned on one layer, which was the F1 layer, which had that first F1 surface that we used. And I'm going to hide all the other meshes, and I need to organize all the meshes that belong to F1 and put it in the F1 layer. So I will accelerate this tutorial a little bit here just for you to see that I'm selecting bit by bit all the mesh patches and organize them into layer F1. And so it requires some inspection. We are working on an automatic script to do this, and the folks at Rhino are helping us with that. So even this tedious part will be automated shortly. But for now, I've done that manually. This is quite a departure from the original way in which we used to use Rhino and KUBRIX. If you follow this process of first turning all your meshes into surfaces and then creating this non-manifold merge using the test extend slits and pruning that non-manifold surface and meshing it, then welding and exploding it, you obtain these bits and pieces of meshes that then we organize back into the layers that we had, and that with KUBRIX will ensure that the face groups and the zone groups that we obtain in FLAC3D are exactly those that we defined during CAD. That's very important, this associativity. That is, a mesh group is associated to a closed volume in CAD, a face group or zone face group in FLAC3D is associated with a surface in CAD. Same thing, a joint in 3D will be associated with a surface in CAD. So I'm very quickly going through all the process of organizing this thing. I'm going to cheat here by moving very quickly through the various stages here. This is by far the longest portion of this video, where we are organizing these various faults, portions of fault into this. So now what you can see here, all these different colors correspond to exactly the surfaces that they came from. So we have as many of these surfaces as we had original, we have as many of these mesh groups that we had original surfaces, or actually original meshes in the data that the client had provided us. So nothing has changed. This mesh that is in front of us is composed of an outer mesh plus a bunch of meshes that correspond to F1, F2, F3, all the way to F9. Now I export all these surfaces as STL files. So I will end up exporting essentially 10 STL files, one for the outer.stl and For each layer, I select that layer and I say select objects, and all the meshes that are in that layer are exported as f1.stl, and all the meshes that are in the F2 layer are going to be exported as f2.stl. And I'm going to accelerate this here, f2.stl, f3.stl, etc., etc., all the way to f4.stl, etc., and we go on. So we end up having a collection of STL files that correspond to the surfaces that then we would like to see as FLAC 3D face groups. Again, this is quite a departure from the earlier approaches to meshings, and really the application of this is mostly for mining application. This is one of the novelties of KUBRIX 15, this associativity. In KUBRIX then, note that we will run the KUBRIX, click on the KUBRIX icon, the dialog box will come up. As the input we will select outer.stl, and on the extra keywords or new keywords we place -fault f1.stl, -fault f2.stl, so on until -fault f1.stl, and as we proceed we run KUBRIX here, and you can see here -fault f1.stl all the way to -fault f2.stl. This whole domain has been increased in size, so this works well. And we click on compute. KUBRIX runs and says right away that it has run f1 all the way to f9, and in this case I'm producing a tetrahedral mesh. For a TET split it will work the same, and the surface is meshed. Any messages about bad intersections and so on should appear at this stage, which we don't see any. We are lucky, but also the process that we chose makes it possible to be very streamlined and produce meshes that are correct right off the bat. The surface is remeshed as it's usually done within KUBRIX, and a tetrahedral mesh is generated, at the end of which a very quick statistics about what's the shortest edge length and what are the worst elements in terms of volume, where are they located, from the worst all the way to the 10th worst. We are going to now bring up FLAC 3D and read this mesh that we generated, which comes out by default as KUBRIX out.FLAC 3D. This mesh is read. You can read it directly from file open in FLAC 3D. You don't need to go to grid, and the grid is read and displayed on the screen as a zone plot item. Right away you can see that clearly all the zone groups comply with the geometries in a boundary fitted way, which is what we wanted. I turned off a few of these groups interactively for you to see that these are all separate groups, but often the boundary of these groups define surfaces. You can use range or wrap command to extract the surfaces that become interfaces, but there are here intermittent faults that are not really boundaries between two different groups. So I would like to see also a plot item of face groups that was produced through this mesh, and we will do that by going into zones and face group. I created just a zone group here in transparency so you can see the context in which these various groups are located, and now we ask for a plot item of face groups. I select face groups, and you can see that 10 face groups are produced, in each with the same name as the file that were used in KUBRIX. The outer one is essentially a redundant one. I'm just turning it off in the color section. So these are all separate face groups that are within your FLAC 3D model. You can do whatever you want with these faces. You can use this face group as range command for applying hydrostatic boundary conditions or roller boundary conditions if they are flat or not. But here we are going to, in the FLAC 3D command, in the FLAC 3D data file, we're going to take these face groups and do a separate and then promote them to interfaces. which is what is explained in the tutorial, and you shall get shortly. Going back to the last couple of slides left in my presentation today, what we provide here with KUBRIX is one that is really specialized to our application, mostly mining application in the area of civil engineering. Here you can see that the same model of a tunnel excavation is meshed here using KUBRIX Block Ranger, KUBRIX Tetra, KUBRIX TET split, where tetras are split into hexes. It's a non-structured hex mesh. KUBRIX Auto Hex, and then KUBRIX Auto Hex again with another setting of the mesh structure. Overall, KUBRIX 15 will be available at the end of this week. We just finished a beta testing period, and a few questions were raised that we are addressing, and the new version of KUBRIX will be posted at the beginning of next week with the proper tutorial that goes with it. So overall, KUBRIX 15 is an interactive and automatic hex meshing tool, and you know, it's a balance between control and automation. Really, the balance is yours. It's yours to choose, and we are available to provide guidance in terms of helping you clean up geometries or produce at least a stub of a mesh, of a meshing process, so that you can carry out the rest of the work by yourself. So you're not alone, and we hope that it is a cornerstone of a reliable and cost-effective workflow. Thank you very much, and please don't forget to address your questions to me by email. My name is Reza Tagavi. I support KUBRIX at Itasca, and my email is tagavi, T-A-G-H-A-V-I, @itascacg.com. And thank you very much for your attention.